Hey, good evening, everyone. Am I audible?
Yes, sir.
Yeah, okay. So if my noise breaks in between, just message me on the chat because I'm in a no network, low network zone. It might happen that we might lose connectivity. Okay, so let us start week 11. I'm Abhimanyu, and this week we will be going through the partial differential equation. So first we will look at the difference between ODE and PDE, then the classification of PDEs. Then we will look at some solution approaches, and then I have two practice problems that we will code. And then I will go through the non-graded assignment. So actually, I've solved the non-graded assignment, and most of the solutions are not matching. I think there is some error in the range of solutions given on the NPTEL portal. So yeah, but anyways, we will code it. We will see. Before that, if you guys have any doubts, then we can start with that.
Sir, you have already told that the doubt is that the solution are not matching in NPTEL portal. That's only the doubts.
Yeah, actually, I did it this afternoon only. So none of the solutions are actually matching. One or two are
Yeah.
matching, but that is probably because the values are so low that it does not matter. But for high values, it's not matching.
And also, that's okay. But in second example, which approach you have applied for the forward difference
Yeah.
or
So what I'm doing right now is I am trying to use the central difference for node three, and for the all the other nodes, I'm using the backward difference itself. Because if we have been given the Newman boundary condition at that end,
yeah, there is no other boundary.
then we could have used the backward difference approach. But with the Dirichlet boundary condition, it's not possible to use backward differentiation at that point.
For that, if you have used that central difference, then that answer is matched or not again for the second example.
No, 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 no. I don't know. It's actually far by a lot of margin. So I think they have
Yeah.
because okay. Let me share the screen. Uh, sure.
Shall I share my code with you to verify that is it correct or not? So I will.
I will show the code to you guys, and then we will discuss
Okay.
it. Uh, problem that was problem two, right? Yeah, problem two. Uh, just a minute. Uh, yeah, so what I have done is these are details are same like discrete L is equal to 1. And discretization, we are taking 50 intervals. H is L by N, Z is 0 to L, T span 0 to 5. I'm initializing the matrix with the zeros, and at one end I'm taking C1 as 1, which is given to us, and that's it. So this is my initial condition vector. It's zeros from 2 to end. Yeah, fine. Yeah, so this is my function. These are my parameters. Dc by dt 0. This is the first node. This is the node. Yeah. Then from 3 to n plus 1. From the third node to the all the way up to n plus 1 node, I am considering backward difference formula. So I'm getting this minus u c I minus 2 minus 2 ci minus 1 plus ci divided by h square plus k ci divided by k plus ci. Yeah, so this is what I'm getting. Then for the second node, I am using this central difference, simple central difference. So that would be ci plus 1 minus 2 ci plus ci minus 1 divided by h square plus k ci divided by capital K plus ci. And then my f values from 2 to end. End is basically my n plus 1, 1 plus 1th node. I hope this is the same code that you have written.
Yeah, yeah, correct, correct. But I didn't use that last D at node 2, so I will try that by using central difference.
So what have you used right now? Forward difference.
Nothing, because I was stuck there and I didn't solve that.
Okay. Yes, I will run this. Yeah. So now we need C value at Z is equal to 0.2. So that would be 11th node. My C solver. Yeah, so it's giving me 9 values. Something is happening. Uh, yeah. So it's becoming unstable. Initially, it is the first one is 000 only. Then from the second one itself, it's becoming a very high values. It's becoming unstable. Probably there is some issue with this. Either it's the values or something, but there is some issue with this problem. Still, it's non values only. Values are becoming very high, so that's why it's giving me non. Mm. Okay, let us use forward difference here. Then let's see what happens. So, what should be the formula of forward difference? T C I plus minus C I on H plus 2 minus minus C I plus 2 minus. Okay, so that should be 4. See, still non values. Something is off with this problem. Yeah, using both forward and backward difference, I'm getting the same nan values. You guys also try. I think you will also get nan values only.
Second example, I didn't try because I was stuck there. So I only try first and third.
First and third, I also did. Just a minute. It should be C3, C2, and C1. I minus 2, C1. Yeah. So this is central difference. Comment this. This is also nan. There is some issue with the problem itself. The parameters are not correct. Something is there. Minus 1. Okay, let us just change this to okay, 0.1. Why is it exploding? It's exploding. Even if I use forward difference, even if I use central difference, it's exploding every time. These all are very high values. Ci plus 1 minus 2 Ci plus Ci minus 1 h square plus k Ci k plus Ci. This is correct. C3 minus C2 plus C1 C2 plus k C2. This is correct. For C n plus 1, I am using backward difference. So this is for the backward difference. FLC2 to end. Yeah, the problem is exploding every time. Also for problem 1, so yep, same issue
Yeah.
with problem 1. It's not a,
Okay, sir. Can you show third example code, please?
yeah, okay.
I have to
Third
replace.
example also, it's not matching.
But how we have write that last condition D10.
Yeah, so what you need to do is that based on this condition,
Basically,
you will get
Tn plus 2 is become Tn same, no?
yeah, Tn plus 2 becomes Tn. So when you write dt by dt at n plus 1th node, so in the central difference itself, for ti plus 1, so that means Tn plus 2. You write Tn, you replace that with Tn, so you get like it becomes 2. You get a 2 outside.
Yeah,
The
yeah,
rest of
correct,
the
correct.
equation remains the same.
Same thing I have did, but still my solution not
Yeah,
match.
it's not matching. It's not matching.
Okay,
I
okay.
don't know what they have done with this week's assignment, because
But
this one of the solutions it's matching, but others are not matching.
what's
Okay,
happened now? Because of this,
find
we
P
can't.
solve.
What we can say? Uh, there is no confidence built to solve the assignment of
Yeah,
not getting confident.
yes, that is the issue.
Okay,
Three
no
six
problem.
five eight. Mm, five. 49.9196. You must be getting these values only.
Just 1 minute, I will check. Uh,
1 and ninth one. Six. Only the first one is matching because the range is very large for this one.
I am getting 80 degree for first answer. 80 degree.
Hello. Uh, what?
I got 80 degree for
Hello.
0.2.
Just a minute. Yeah, Nilesh, what were you saying?
I'm saying that for this example, I got an answer at 0.2, 80 degrees Celsius, 80 degree, 80 point something. I don't know why. So,
Mm, okay. So we can check the code.
No, just 1 minute. I will check it. H square by 2 plus h power n plus 1 minus same code I have written here. 22 and yeah.
You can share the code in chat and we can see.
Just 1 minute. I will share.
Similarly for problem 1. Six party is 20. Plus 1 minus 25. FLPD function 100 square into ti plus 1 minus 2ti plus ti minus 1 0.2.
Instead of h bar, I have taken m.
Yeah, that is fine. Span 0 to 2. This looks correct to me. Let us run this. See, I
At 2 because you just I have just plotted 9 values, 9 which shows 80.
see t t0 to 2 and t span 0 to 2. Span 0 to 2 is equal to 10 is correct. T1 plus 1 T0 to 2 1. It's basically the same code. 0.05 0.05 H by 0.2 L. Okay, I think this. I think your n value is different.
No, that's
That's
length of
10 only. Fine. Mm-hmm. H is n by n, T 100. And why is it giving different answer?
no.
K divided by H square. So minus 25. Same code. And so I guess we are checking the wrong.
Mhm.
Because I think mine case also I'm getting the same thing.
Same. That is like 69.69 point something is for
Yeah,
0.3
third
maybe.
node.
Uh,
Hmm. Yeah, they have the ranges they have used is wrong, I think. Because for the
yes.
first case, the range is very large, so that's why we are getting correct answer.
Okay, so shall we proceed with our final assignment? I don't understand what.
What?
Is there any what we can say? Is there any way to connect with our in that NPTEL team, or what we can do?
You just need to you can
Mail
mail, not mail. There is this there is
for
this
discussion forum.
yeah, discussion forum is there, right?
So I have already posted
Because
that.
yeah, because these graded assignments and non-graded assignments, these are taken care by the TAs. So
Yeah,
those
okay,
TAs
okay.
are different than us. So we don't take care of these things.
Hmm. Okay, sir, no problem. Start your whatever your schedule today. We can start, sir.
Yeah, okay. Uh,
Thank you. Thank you.
Bhavesh, do you have any doubt? Okay, fine. Yeah, fine. So we were just discussing about PDs. I think you guys already know. So PDs basically have yeah. So PDs have two or more independent variables, and ODs have single independent variable. So like in OD's case, we have del, not del. So dt upon dt is equal to f of t only, right? So it's a function of t. We have only one independent variable, whereas in the case of PDs, we have something like uh, plus dt upon dx is equal to some function of t comma x. So in this case, we have two independent variables t and x, and so our solution of f depends on both variable x as well as solution for t depends on both variable x as well as variable t, which is time in this case. Um, right? Yeah, so we have like these different cases. First one is the rod conduction in steady state. So let me write the equation for the transient case first, and then we will go to steady state. So for transient state, we get something like del t upon del t is equal to t upon del x square minus t minus t. In this case, we have a heat loss to the surroundings, so that is why this term is coming. And this is just the heat flow across this rod, and this is the change in temperature with respect to time. So so this is a transient PD. Why transient? Because we have this time derivative in here. Once we let the simulation run for long duration, then these time derivatives die out. So we get there is no further change in the rod with respect to there is no further change in temperature of the rod with respect to time. So this term becomes zero, and then that is what is called steady state. So this whole equation is for the transient state, and then after a certain time, we are only left with this part of the equation, and then it becomes a steady state solution. Similarly, like this is for 1D for 1D case. Similarly, we get for 2D case. So in 2D case, we get term like I take this as x and this as y. This will be my dy square, and plus if there is some heat loss, so we get uh, should be minus some terms. This is just heat loss due to convection or conduction, whatever. No, this is heat loss due to convection or radiation, and this is due to conduction, the heat flow across this plate from this direction and in this direction. And once we let it run for long duration, this terms become zero, and we get this these equation only. And if we remove the heat loss, then we simply get the equation. I think it's called the Laplace equation. Yeah, so we will see how to solve this transient problem using normal method of lines, and then we will see how to do this using FDM, forward in time and central in space. Mm, yep. So the next part is the classification of PDEs. So this is a general structure of PDE. If we have this F term, then it's called inhomogeneous or non-homogeneous PDE, and if this F term becomes zero, then it becomes a homogeneous PDE. This is similar to the case of ODE, where in case of ODE we have like d phi upon dt plus so this should be t, and if we have some term over here, then that becomes non-homogeneous or inhomogeneous ODE, and if this term becomes zero, then that is a homogeneous PD ODE. Okay. Mm. Similarly, for the case of PDs also, if this F term becomes zero, then it's a homogeneous PD. Now we can classify these PDEs into three parts: elliptic, parabolic, and hyperbolic. How do we do this is we get this, we write PD in this form, and then we just need to look at the coefficients of all the second order terms. So these three are the second order terms, these are first order terms, so it does not matter what the coefficients of these first order terms are. Uh, why is it so? Because we can sort of treat this as quadratic in, like, if I consider this whole term as x, this whole term as y, and this whole term as xy. So we get something like ax square plus bxy plus cy square, and then I have some more term dx plus ey plus f is equal to 0. Now for the time being, if we neglect these terms, so we get ax square plus bxy plus cy square is equal to 0. Okay. Now we need to check for this condition. Okay. B square minus 4ac. We have three cases: positive, negative, and 0. If it's less than, if it's positive, then that means it's hyperbolic. If it's negative, then it means it's elliptic. And if it's 0, then that means it's uh, parabolic. Now we can easily see the parabolic case. B square minus 4ac is equal to 0. That means either this whole term like this difference becomes 0, or another case is either b is 0 and any of one terms a and c is 0, right? So either a or c, any of these terms are 0. So basically what is happening is this is becoming 0, and if I take any one of the term 0, so let us take a as 0. So we are left with equation cy square plus dx plus dy plus f is equal to 0. This is basically the equation of a parabola, right? So simplest term, we have equation like uh, y minus a whole square is equal to 4 uh, x minus b, something like that, right? Mm. Yeah, so this is basically the equation of a parabola. And similarly, we can see other cases. So if b square minus 4ac is negative, right? So in other, I just clear this. So I can also write this as a equal to equal to zero, right? So now this b square minus 4ac is basically determinant of this thing. And you can see that this is equation of if it's less than 0. Like this is basically the equation of a hyperbola or a ellipse. The only difference is the coefficient of a and c. So if both the coefficients are positive and b is very small, then b square minus 4ac becomes less than 0. If any of these coefficient a and c, like either of them is negative, then this term becomes positive and b square minus 4ac becomes greater than 0, right? So if any of these terms becomes negative, then what happens is you get equation something like ax square plus bxy minus cy square is equal to 0. So this is basically your equation of a hyperbola, right? X square upon a square minus y square upon b square is equal to 1. So this is basically your hyperbola. And x square upon a square plus y square upon b square is equal to 1. This is your ellipse. So if this is less than 0, that means both a and c are positive, and b is less than 4ac. So that is we can simplify this equation to something like this, right? So it becomes an elliptic PD. Whereas if either a or c of either of these two are negative, then that means b square minus 4ac is greater than 0, and we can convert this into something like in this form. Not exactly this, like we will have some shift in origin, so we might get something like x upon a whole square upon a minus y upon b whole square upon b square is equal to something 1 upon c square something. But this coefficient will become negative and it's a hyperbola. So similarly, this becomes a hyperbolic PD. Okay. Any doubt in this? How we are doing this classification? We just need to check the coefficients of all the second order terms. The first order terms, they don't matter much. They just provide a shift to the origin of this entire PD. Okay. If I do a geometric representation, then these terms just provide a shift to the origin. They don't add any new information. Right. So let us look at these, like what sort of PDs these are. Just clear this. Let us first cut the steady state down. So we have del t upon del z square is equal to L t minus T. So we need to check A, which is square, B, which is del square phi upon del x del y, C, which is del square phi upon del y square. Uh, yeah. So in this case, it's like either I can take this as A or I can take this as C. But we don't have any B in this term, right? So I can take A as 1. So my B square minus 4AC, C is also 0. This is also 0. This becomes 0, right? So I can say that it's a parabolic 3D. It's not exactly, yeah, it's not exactly parabolic. Something like I square is equal to, I have some term, not exactly parabolic, but yeah, based on the classification, we can classify this as a parabolic PD. If I look at this transient case, for this also the equation is del t pi upon del t uh, equal to del square t upon del z square minus beta t minus ta. Yeah, so a is 1, b is 0, t is also 0. So for this also I'm getting b square minus 4ac as 0. So this is also a parabolic PD. Right. Similarly for the conduction in plate, uh, so either if I take the steady state or the transient, it does not matter because this term del t upon del t does not contribute anything. We just need to now look at these three terms. So for this case, it is like del square t upon del x square plus del square t upon del y square is equal to 0, or or I can write del t upon del t, but then this does not matter. So I have a as 1, b as 0, c as 1, right? So my b square minus 4ac becomes minus 4, which is less than 0. So this is my elliptic PD. Also, I can simply, you can see, right, if I take del t upon del x as my capital X and del t upon del y as my capital Y. So this becomes like x square plus y square is equal to 0. Like even though it's a equation of a circle, but circle is also part of ellipse family only, right? So this is an elliptic PD. Okay. Any doubt in this classification part?
No, sir, it is clear.
Okay then. Yeah. So these are some of the PDs of interest to us. Like we have the Laplace equation, which is an elliptic PD. So this is basically our steady state, steady heat conduction in 2D. Or even in 1D, we can say that it's in 1D also it's Laplace equation. So in that case, our phi is simply 1D variable. Like it's a simple scalar, not a vector. Uh, then we have wave equation, which is a hyperbolic PD. Yeah, so we can see that it's d square u upon del t square. Just a minute. Take a call. And then we have minus c square del s square u upon del x square is equal to 0. So if I write this, like, I can take this x square minus c square y square is equal to 0. So this is basically a hyperbola, right? So this is a hyperbolic PD. Also, we can see that a is equal to 1, c is equal to minus c square. So b square minus 4ac becomes 4c square, which is greater than 0. Okay. So this is a hyperbolic PD. Then next is heat equation. So if this is a parabolic PD, both a and b are 0, so we get b square minus 4ac as 0. So this is a parabolic PD, and then we have Poisson equation, which is also again an elliptic PD, because this does not matter, and this should be a phi in here, and this is basically yeah, this is basically del square phi upon del x square plus del square phi upon del y square is equal to f xy. So this does not matter, and these two are a is equal to 1, c is equal to 1. So let us now look at some of the solution approaches. Like, we have different cases. We have hyperbolic PDs, we have parabolic PDs, we have elliptic PDs. So like in OD, we just simply use the same OD 4-5 solver for everything. We just convert second order PDs into second order ODs, or higher order ODs into first order first order ODs, and then we solve using OD 4-5. So that does not work in here, because like all the different types of PDs use require different approaches. We have PDs in space, like the Poisson equation or Laplace equation, and then we have PDs in space, in time and space. So both of these needs to be solved using different approaches, right? So we have different approaches to discretize the PDE. One is the finite difference method, which we will see. The other two are finite volume method and finite element method. So finite volume method is mostly used in CFD analysis, and finite element method is basically used in FEA, it's like finite element analysis only. In structural simulations, we mostly use the finite element method, whereas for the computational, like fluid dynamic simulations and fluid dynamic analysis, we use the finite volume method. We will look at some finite difference, like solve some of these PDs using finite difference approaches in this lecture. And then we have the method of lines. So this is basically, we are discretizing the entire domain into smaller lines, and then we solve on this line, like we solve this line as a OD. We solve for these small lines, we solve as a OD, and then we combine all these solutions. We combine all these solutions at these nodes to get the final solution of our PD. Okay. Fine. Uh, so first, let us look at method of lines for transient PDs. So we have this equation for so we have this equation for transient PD, heat conduction in a rod. We have the ambient temperature is TA, so we have some loss due to convection to the surroundings, so that is being captured by this term. And then this is the heat flow across the rod, and then this is the time rate of change of temperature with respect to time. Yeah, so what we do is we basically we discretize this domain into smaller elements, smaller subdomains. Then for this a small element, this we can convert this into, we discretize this equation using finite difference method for this straight line. So we get something like dti upon del t is equal to alpha, and we can use any of the discretization scheme. The most used one is the central difference, because it's simpler and much more like the error tolerances are also higher for central difference schemes as compared to forward and backward differences. So we get something like so now this is basically a ODE in terms of TI. So similarly for the other line we get another equation, and likewise we get, if I am discretizing it into 4 domains, then I will get 4 ODEs. And then each of these ODs are coupled, because this Ti plus one, this Ti plus one I will be getting from the next. So if this is my node 1, this is my node 2, this is my node 3. So for this is my node 4. So for this element, for this node, I need the temperature from this node and the temperature from this next node. So basically this node, the OD for this node is, this element is coupled with the previous element as well as the next element. So we get these 4 coupled ODs, right? And we solve this using ODE 4, 5, and we get our solution, and then we combine the solution to get the final result. Okay. And also, since this is like we have one time derivative and one space derivative, so we need like it's a second order derivative in x. So we need 2 boundary conditions, and it's a first order derivative in time. So we need one initial condition. Okay. So that is what is given to us. Boundary condition is rod at one end is held at 100 degrees. So this is, the one end is at 100 degree and the other end is at 25 degrees Celsius. And the initial condition is the entire rod is uniformly at 25 degrees Celsius. So the entire rod, the temperature is 25 degrees Celsius initially. Okay. Fine. So let us see how to code this. Mm. So this is through method of lines. I am okay, let me discretize it into 10 parts. So my length of the domain is 1 meter. I'm discretizing it into 10 parts. So my h would be L by 10, that is 0.1. And then this is my node locations. The parameters are given as 0.025 value of alpha and beta is 0.1, and the ambient temperature as 25 degrees Celsius. Yeah, so this is the initial condition. Since we have given an initial condition like the whole rod is at 25 degrees Celsius, so I will initialize all the nodes with the ones, and then I will just multiply it with 25 to get a vector of all 25 degrees Celsius values. Okay. The first element of this should be 100 degrees Celsius because that is the initial condition, and the end node is maintained at 25 degrees Celsius. That is given to us. So we will change these 2 elements of this T vector. And then since these 2 elements are already fixed, the boundary conditions are there. So we just need to solve from the second node to the nth node, right? So suppose I have discretized it into 10 elements. So I have 11 nodes, so I am only solving from the second node to the 10th node. The first and the 11th node are fixed. Okay. My T span goes from I'm solving it for 5 seconds and is in increments of 0, 0.005. 0.0005. Let me just make that 500. My system is a little bit slower. Mm. So this is just solving using OD45. These are my this is my function. Yeah, I'm passing on all these variables. So my dt by I initialize my time derivative vector with with zeros. The first node I know that it's at 100 and the last node I know it's at 25, and my I only need to solve for 9 nodes. So that is I'm storing the y in my, like, I'm storing, assigning the temperature from 2 to nth node with the y values. Okay. Yeah, so this is like this is the equation using central difference. So alpha times, yeah, so alpha times ti plus 1 minus 2 ti plus ti minus 1 divided by h square, and then minus beta ti minus ta. So this is I am doing from second to nth node, and then my f value is only from second to nth node. The first two dt by dt values are not important because we're not solving for them. And then I am simply
Excuse
using
me, sir.
OD4. Yes.
Sir, this initial condition that is
Yeah.
given, uh,
Yes.
that should be value of temperature at time is 25-degree uniformly, means throughout. So
Yes.
that condition is applicable in the outside of the function. Am I right?
Yes, that is applicable outside of the function. So that is what I have done. So this is my initial
Oh,
condition assignment, right?
uh,
So T0, I am initializing my T vector to all 25. So all the values are 25 initially.
okay,
I am changing only the
okay,
first and last node, right? So this T0 I am providing as input to my OD45. So this is my initial condition, right?
okay, sir. And
This
and
T0.
and the boundary condition is applicable within the function body. Is it true?
Yeah, boundary condition should yeah, it's applicable within the function boundary because those two values are always fixed, right? So even
Okay,
if we are changing everything else with time, these two nodes are always fixed in time, right? So that is
okay,
why
sir.
boundary
Okay,
conditions, we fix these values inside the functions.
okay, sir. Okay,
Actually, if these values are not used inside the function, then you don't even need to use them inside the function. But since we are using central difference scheme, so for the second node and for the nth node,
yes,
we need
yes,
this first and nth plus one node. That is why we are using we are
yes, sir. Yes, sir.
defining these values inside the function.
Yes, sir. Okay, sir. Thank you.
Okay, yeah. So I will just run this. What was the value? The plot. Yeah, I need these codes on my lab system. That system is faster. It takes time on my laptop to solve this.
Okay, sir. No problem.
Just plot it like this. Build. So so this is the temperature that I'm getting. Mm, so it starts with 0, and then at the last node it remains at 25, and for all the other nodes, okay, let me don't do draw now, then it should run. Oh, this. Uh, so the issue is that we don't have enough nodes. So I'm taking an increments of 200, whereas my T span is only up to 100. So it's not even entering that loop. Should run. Yeah. So the first one is for T is equal to 1, T is equal to 2, 3, 4, and 5. So last one is for T is equal to 5 seconds. So we can see how the temperature changes. If I also plot 0. Yeah. So this is how we initialize our system. The first node at 100 degrees Celsius and all the other nodes at 25 degrees Celsius. And then as time progresses, we get finally the green line, the green, yeah, the green, not the green line. Should So finally we get this blue line at t is equal to 5 seconds. Okay, and I can even run it for more duration. Remove this hold on. I run it for 10 seconds. So you can see how the temperature I hope you can see the animation, how the temperature changes with time.
Yes, sir. Yes, sir.
Yeah. Okay. So we start with this, and then at t is equal to 1, like this, it changes, and then it becomes after a certain time, it reaches a steady state. Fine. So now let us solve the same problem using finite, this one. So we will use the finite difference method for the same problem. So we'll explain the code first. The first part is same. We are just discretizing. So notice that in this case, we were discretizing only in x in the z domain. We were not discretizing in the time domain. That was already taken care by ODE45 implicitly. So it solves that inside itself, and then it gives us some output at all of these points only. But the internal time stepping that happens automatically, right? So if I don't give this t span, if I just give 0 to 5, yeah, we'll stop the. I think I should stop the plot. So now you see the T-sol, I am only getting a 73 cross 1 vector. So initially what I was getting at as 2000 for the same uh, for same 0 to 5 also, if I was getting 2000, if I don't give these values implicitly, then it takes as like it takes 73 only 73 time steps inside the ODE45. Whereas in FCTS, like infinite difference method, we are discretizing both in x in z domain as well as in time domain. Okay, so I am doing 50. I am discretizing it into 50 elements in z domain, whereas in time domain, I'm using very small time steps. So I'm discretizing 5 seconds into thousand sub parts, and then I'm using finite difference at all of those 1000 parts, right? So these are my parameters. This is simple. And yeah, these are my initial conditions. So same as before, I'm initializing everything with 25 degrees Celsius. And these two are my boundary conditions. So at one end it's 100 and at the other end it's 25. Now we are using a FC FT, what is it? FTCS, forward in time and central in space. So that means for the time derivatives, so if we discretize this dt by dt, so we are discretizing this using forward differentiation scheme, and then d squared t upon dx square, we are using a central difference scheme for this. So that is why it's called forward in time and central in space. So this is a space derivative, and we are using a central difference scheme, and this is a time derivative. So, and we are using a forward difference scheme. Okay. So, okay, let me go. I can write it over here only. So let me just type. Yeah. So it becomes. Um, STI divided by dt is equal to. Yeah, alpha multiplied by. So this I am using central difference. So I will be getting p I plus 1 minus 2 ti plus ti minus 1, and I multiplied by h square, and then minus rest is same, beta ti minus ta. So now I will take this dt to this side, so that this now becomes my alpha into dt divided by h square. That is the coefficient of these terms, and then this becomes beta multiplied by dt. Okay, and I also take this I to this side. Yeah. So one more thing to note here is that this ti plus 1, this ti plus 1 is not same as this ti plus 1. This ti plus 1 is okay. Let me go to whiteboard only. Mm, So we had these two terms. This we had discretized at I plus 1 minus Ti upon delta T is equal to alpha Ti plus 1 minus 2. And okay. Now suppose I'm going from T is equal to 0 to T is equal to 0.1, right? So all of these elements uh, and this element. So I will be getting something like this. Ti plus alpha delta T upon h square. I will get all of this term over here plus not plus minus beta Ti minus Ta and delta T. So now all the T terms that which are on this side, these terms belongs to T is equal to 0 second, and this Ti plus 1, this belongs to T is equal to 0.1 second, right? So this is forward in time, and these all belong to a later time step. So this is like an explicit scheme, because these Ti don't depend on do not depend on the Ti plus 1, which is yet to be calculated. Uh, if I convert it into an implicit scheme, so in that what happens is that Ti plus 1 Ti plus alpha delta T upon h. So now if this Ti also belongs to the current time step, then this becomes an implicit scheme. So for that we need to use some sort of like F solve or Newton Raphson, some iterative solving schemes. For this we can simply use the Gauss elimination to solve this, whereas for this we need to use some sort of iterative schemes. So we need to give an initial guess for Ti, and then we wait for all the temperatures to reach a steady state or settle down for the current time step, and then we move forward in time to next time step. We don't need to do all those things in this explicit scheme. So that is why this explicit scheme is faster as compared to implicit scheme, but then implicit scheme is much more stable, because we are using an initial guess, and then we are converging to a stable solution for that time step and then moving to next time step. So this implicit scheme is stable as compared to explicit scheme, but it takes time. Okay. So this is the case everywhere, like wherever we are using our implicit solving scheme, which means that the values of the current time step uh, depend on the like we are using the values of current time step to calculate the current time step, right? Uh, that is always stable, but it takes time because we need to use some iterative solvers. Whereas for explicit, to calculate the values for current time step, we are using the values of previous time step. So it's a bit faster, but then mm, there are issues with the with convergence and stability. Yeah, so I hope this is clear. Now let me go back to MATLAB.
Yes, sir. Yes, sir.
So basically, this is my yeah. So what I have just mentioned, this Ti we get Ti plus 1 plus alpha times dt. This is my central difference divided by h square minus dt times beta and then Ti minus Ta. This all is same, and then I get this Ti. So this is for the all the values corresponding to previous time step, and I'm using these values to calculate the T new like the temperature at ith node for the current time step. And I continue to do this for like up to till 5 seconds. I think yeah, 5 seconds. It is till 5 seconds. Yeah. So up to 5 seconds, I continue to do this. and then I'm just plotting. So we solve this equation. Yeah, also you will see that we are not checking for convergence. We are just initializing this temperature with 25 degrees Celsius, and then we are simply running this explicit time scheme. Okay. Mm. So if I run this, and yeah, so this is what we are getting from the FCTS scheme. The last one is for t is equal to t is equal to 5 seconds, and then if I superimpose my results from the method of lines solution, it should superimpose. Let us lines. Mm, Hold on, plot it on further one. Yeah. Yeah, I hope you can see the screen.
Yes, sir.
Yeah, so you can see we are getting like the solution from method of lines and the from FTCS scheme, finite difference scheme, we are getting the same solution. The difference that you are seeing over here is because we have used very small discretization for the finite difference method. That is why there is no overlapping over here. But for the most part, you see that both the solutions are similar in nature, or we get the converging, we get the overlapping solutions in both the cases. Mm, yeah, fine. So this is like for the transient case. So method of lines for transient PDEs. Next is method of lines for hyperbolic PDEs. So similar to the earlier case, we discretize the scheme. We discretize this equation. So I think I have some. Yeah. Fine. So this is the basic part. Discretizing the length in 50 elements. Initial condition, like we have been given that at inlet z is equal to 0 for all t, theta in is equal to 1. So yeah, so this is like my boundary condition, theta in at so this is like my theta at node number 1 is equal to 1. So I will just initialize my theta vector to theta in and then y. So all this y is basically from the second node to nth plus 1 node, and this theta in is my first node. And then my initial condition is at t is equal to 0, theta 0 is equal to 0. That means theta at time t is equal to 0, all the theta values are 0. So this initial condition is basically here. Okay. And then I'm using a t-span value, like I'm just putting my result at t is equal to 0, 0.5, 1, and 5 seconds. This is my OD45. So y0 I'm taking from uh, yeah, so I have like n plus 1. Okay, let me is confusing. So we just zeros plus 1 comma 1 if 1 is equal to theta in my n is equal to 1. Then my initial conditions becomes theta from 2 to n plus 1 comma 1. Okay. Yeah. Fine. So for the node from node 2 to n, I'm using simple central difference scheme. So you will notice that this is not a second order term, it's a first order term. So I get theta I plus 1 minus theta I minus 1 divided by 2h minus k theta I. And for the nth plus 1 node, I'm using backward difference because I don't have nth plus 2 node over here. So I'm using backward difference for that node to calculate the derivative. And the rest I'm just taking from my d theta from second to the last element, and I'm getting dy. Then I'm just integrating this. So and this, yeah. So we get these advective terms, like the last one is for t is equal to 5 seconds. Okay, let us plot this for more time domains. Yeah, so even though the this red line has t is equal to 1, then the yellow. Yeah. So this yellow line is for t is equal to 2, and like eventually, even though the solution is nearer to the final steady state, we get these oscillations around the point, around the steady state, because of using the central difference scheme. Usually this should not happen in PD, in like in any of these hyperbolic PDs, because you can't get a solution which like, even though the solution can oscillate around the steady state, with respect to time it should not. So if you get a solution which is similar to this, that probably means that you are doing something wrong. Either the discretization scheme is wrong, or you have made some error in your overall function for the code, for the problem. Okay. So I will just solve the same problem using backward difference scheme. So we don't need to change anything. We don't need to change anything. Just at this endpoint, not the endpoint. Endpoint remains the same. Just the middle nodes from the second node to the nth node. We will change from central difference scheme to backward difference scheme. Okay. In central difference, what is happening is that for the ith node, you are using the current node. No, you are using the node before the current node and node after the current node. There is only this theta I which is responsible, which is giving some input to the derivative for the current node. So that is why the solution is oscillating, because it's trying to match the previous node as well as the next node, but the effect of the current node is not that much. Whereas in backward difference, we get this theta I and then theta I minus 1. So there is no dependence on the next term, like theta I plus 1th term. So it is much more stable as compared to the central difference scheme. For the same values, So we get a much more stable solution. Okay. So we are using the same for the same discretization, for the same discretization, like for the same number of elements n is equal to 50, the central difference is oscillating, whereas for the backward difference, it gives us a stable and non-oscillating solution. Fine. So this is method of lines for hyperbolic PDEs. This example I've already told, and then we are only left with one more example. So I wanted to discuss this wave equation using method of lines. This is also interesting because it's a second order. So up till now, until now, whatever equations we saw, those were first order with respect to time, and they were only second order in a spatial domain. So we were using method of lines to discretize the spatial domain, and we were using ODE 45 to solve the time derivative as a first order ODE. Okay, but for the wave equation, even though the spatial derivative is still second order, the time derivative is also second order equation. Okay, let me back to whiteboard. Yeah. So in previous cases, what we saw was we got something like del P upon del T equal to alpha del square T upon del X square. So this was second order in space and first order in time. So we just simply discretize this using a finite difference method, and then we use method of like we then we got first order ODEs, and we solved that using ODE 45. In this case, what is happening is that this is del square u upon del t square is equal to c square del square u upon del x square. Still, we get something like del square t upon del t square is equal to c square. So I will discretize this using central difference scheme only. So I will be getting ui minus ui plus 1 minus 2 ui plus ui minus 1 upon h square. Right? So now I have a second order ODE in time, right? So to solve this using ODE 45, I need to convert this into two first order ODEs. Fine. So similar to what we have been doing until now for the other like for the ODE cases, in second order ODE cases, we simply take del u by del t as let us take that as y, and then my del y by del t becomes c square del square u by del x square. So del y by del t becomes c square ui plus 1 minus 2 ui plus ui minus 1 upon h square. Okay, so now it's not wrong, but we got from here to here. So now we have this as one equation and this as second equation. Okay, so we can now we can use ODE 45. We have got two ODEs, not two ODEs. So um, I think I have not mentioned the boundary conditions here. So my boundary condition is that I'm initializing with a displacement of u at t is equal u at 0 as 0, u at l as 0, and my initial condition is u at t is equal to 0, and then x is equal to sine 2 pi x. So my initial condition is something like this. These two nodes are always fixed. That is my boundary condition. And at t is equal to 0, the string is like this. Okay. So how many ODs do I have? Boundary conditions are fixed. If n is equal to 10, then I will have 11 nodes. And so this will give me 9 ODs, right? From 2 to n. And this will give me 9 ODs. So in total, I have 18 coupled ODs to solve. Okay. Is this clear? Uh,
Yes, sir.
okay. So we will see this code and then we will end today's lecture. Fine. Yeah, so I am, let us discretize for 10 only. So this is my discretization, same as before. I'm doing my simulation for 5 seconds. So these are my initial conditions. Uh, and yeah, note that the conditions given to us are only for u, right? But since like in all the other cases, like in these cases, in where the time derivative with respect to like with time derivative is of first order only, we get only one initial condition. But in this case, since the time derivative is also second order, so we need two initial conditions, right? So one initial condition is on displacement and the other initial condition is on velocity. So I'm initializing my displacement with sine 2 pi x and my velocity as 0. So I am just uh, uh, like I'm using some method to just keep my string like this and then initialize my simulation with zero velocity. I'm not giving any velocity to the string. Then I'm just combining the state vectors to combining these u and v naught vectors to get the initial condition vector. Also note that I am only taking my elements from second node to the nth node for the displacement and second to nth node for velocity. Because for boundary conditions, I'm assuming like the given boundary conditions is that u at 0 and u at l is fixed. And likewise for velocity, I'm assuming that since the displacement is fixed at those two ends, so there is no velocity anyways, right? Because if I fix two ends, uh, if those two ends are fixed across the entire time duration, then anyway, then eventually the velocity also becomes zero, right? So that is what I'm taking. We will look at the function too. Then that will become more clear. Yeah. So this is my wave equation, function for wave equation. The parameters, I only have one parameter, c value, which I've taken as one. This is just I'm calculating my h value. Yeah. So these are my boundary conditions. u at first node 0, u at ns plus 1 node 0, and then in all the between nodes, whatever y value I'm getting, I'm just using those values. Okay. So yeah, this is like a little bit different because my y contains u and v. Okay. So y1 to n plus 1 is displacement, yn to end is velocity. Okay. So I'm taking my y taking the elements from y to nth minus first element of y to nth minus one element of y, and I'm storing those in u2 to n, and then from n to n I'm storing them in the velocity part. Okay. And these two are my boundary conditions for the nth for the first and nth plus one node. So zero velocity at both of those two nodes. Yeah, then this is just a du by dt I have taken as v here, like velocity, and then dv by dt I'm initializing with zeros, but eventually we will fill it up with the with this wave equation. Okay. So from 2 to nth node, my dv by dt becomes c square times central difference formula ui plus 1 minus 2 ui plus ui minus 1 divided by h square. Okay. And then yeah, so notice that I have not written any dv by dt nth plus 1 because it's already fixed. We know that it's fixed. We don't have any Newman boundary condition on that. It's a Dirichlet boundary condition. And then my f values du by dt from 2 to nth node and dv by dt from 2 to nth node. And then I'm just integrating them using OD45. And this is my plot. I will run this. Just add a pause. And let us increase the number of elements. Yeah. So this will run till t is equal to 5 seconds. Okay. Even though if stop it, it will just decrease this pause to 0.0.25 seconds. So this is our initial condition, and then I'm not giving any velocity, just the initial condition, then it's doing that. We have not used any damping, so this will continue to move. If we use some damping terms, then eventually this will the string will continue to lose energy, and then eventually it will just reach a steady state at u is equal to 0 for all time. Okay. Yeah. Yeah, so this was the other example that I wanted to discuss. I have discussed everything, right? So Bhavesh, now if you have any doubt in any of the codes or anything related to this week, even the previous weeks, then I can answer those questions, and otherwise we can end the meeting, today's discussion.
Sir, in 1 minute, sir, I am checking it.
Yeah, okay.
Sir, in graded assignment number 11, week 11.
Yes.
In problem 2A,
Yeah.
uh, in this problem, the boundary condition can be written as, and one equation is given, a1 yn minus 1 plus a2 yn a3 yn plus 1 equal to b.
Hmm.
So note that since this is central difference formula a2 equal to 0, please rearrange the above equation to get the below one equation. So according to central difference, yn is considered as 0.
Yeah, no, yn is not considered as 0.
Oh,
We are considering a2 as 0 because if you write the central
a2 is
difference
0.
form, yeah, because if
Okay,
yn becomes 0, then that node value basically becomes 0, which is not possible, right?
okay.
The coefficient will become 0, not yn will become 0.
Coefficient is 0.
We need to find. Yn we need to find.
Okay.
Yeah, this is similar to what you asked. This is similar to the non-graded one that we had for the last week, right? This one. So we had this problem, right? So report the values
Okay.
of a and plus 1 and b. So something like that. This needs to be done for that part also.
Okay. We should replace tn plus 1 with that tl.
Mm,
Okay, so here also yn plus 1 is replaced with this.
yeah.
Okay. Mhm.
Okay. Any more doubts?
One minute, sir. In sir, in week 11,
Yeah.
non-graded and last problem,
Yes.
here also the conditions are given that t dash at n plus 1 is 0 and below tn plus 1 minus tn is 0. So,
Okay. Yeah, so what is the doubt?
so what should we consider at to calculate the last node? Because if we use this central difference formula, then at the last node,
Yeah. Okay. So you can see my screen, right?
yes.
So what is happening is that if I use central difference at last node, so I
Mhm.
should be getting something like dt by dt n plus 1 n plus 1 as k multiply, is it k only, right? Yeah. T I plus not I plus 1 n plus 2 minus 2 times t n plus 1 minus not minus plus t n,
tn, yes, correct.
right? Divided by h square and plus other terms h bar, and
Yes.
that will be in tn plus 1, so that is not an issue. Now since it's a Newman boundary condition, so based
Okay.
on Newman boundary condition we know that dt by dt would be tn plus 2 minus sorry, tn plus 2 minus tn n only, right, by 2h. Okay, so this is a Newman boundary condition using central difference at node ns plus nth plus 1, right?
Okay. Mhm.
And now we are given that this Newman boundary condition is equal to 0. So basically this term is equal to 0, right?
0. Mhm.
So what we get from this is that Tn plus 1, Tn plus 2 is equal to Tn, right?
Okay, so it should be replaced with Tn.
Yeah, is
Okay,
equal to
okay.
Tn. So basically in this dt by dt, dt by dt equation, this equation, we just need to replace Tn plus 2 with Tn. So that becomes like 2Tn minus 2Tn plus 1. So we get 2 out. So we get 2k Tn minus Tn minus Tn plus 1 h square plus h bar Tn plus 1 minus 25. So this is the final equation that we will get.
Okay, okay, okay.
Okay.
Yes, sir.
Yeah. So actually the answer is still not matching, but yeah, you get the idea.
Mm.
They have done something with this non-graded assignment. I don't know what. All the ranges are wrong.
Mhm.
Fine then. Any more questions?
1 minute, sir. I'm checking.
Okay.
Okay, sir. Now it is clear. All doubts are clear. I
Okay.
actually felt the problem at the last node because in central difference that n plus 2 comes. So when we divide the total interval in n plus 1 nodes, so that value is missing. T n plus 2 is missing. So,
Yeah, so these like the problems for this week are mostly similar to problems for the last week. So you remember
uh,
you asked the similar doubt during last week
yes,
also.
yes, yes, yes.
Basically the same doubt.
Yes, so that should be replaced with the previous node using
Yeah,
such type of relations. Okay.
yes. So
Okay.
that is the issue that we are having in this problem too, right? They have asked us
Okay.
to use backward difference scheme for node 2 to n plus 1 node and nth plus 1. So if we write the equation for backward difference at node 2, then you need some value of node 0, right?
Yes,
So,
yes, yes.
but we don't
Yes, sir.
like, but
I am feeling the same question here also. The same question here also. When we okay, so uh, if we write the backward difference for second order differentiation,
yeah,
then at
you
the
can't do that.
T3 it is okay, but
Hmm.
okay, when we calculate T3, then what is the value of T2?
Uh, yeah, for third node it's fine, but
Uh,
for the second
yes,
node the issue is there,
yes,
because then for the second node we need the location of the zeroth node, right?
0. Yes, yes.
So that is what I was that is what I was discussing with the other person. I what I have done is I have used the central difference at node 2 itself. I have not used backward difference for node 2, but for the or all the
Okay,
other
okay.
nodes I have used backward difference. If we would
Okay,
have been
okay.
given a Dirichlet boundary condition at c is equal to 0,
Mhm.
then we could have used the backward difference scheme, because then we would get something like what we are doing in this problem for node nth plus 1. We can do something
Okay,
similar for this problem at node n is equal to 2. But
okay,
since it's a Newman boundary condition, we can't do anything. So either use a forward difference for the second node or use the central difference. We can't use the backward difference for that.
okay, sir. Okay. My internet was gone at that time, so I
No,
left sometimes. So I
no issue, no issues,
missed that one.
no issues.
Okay. Okay, sir.
Okay
My
then.
doubts are clear.
Okay then. See you next week.
Okay. Okay. Thank you, sir. Thank you.
Yeah. Bye bye.